let's see how we can give corrections for a non-word spelling error. So we have already detected this error by looking through dictionary. We didn't find this word in the dictionary and we say that it's an error word, non-word spelling error. So now we need to correct the word. For that, first we need to generate candidates. So how we can generate candidates? The most probable candidates would be the words with similar spellings to this actual error. So it has a high possibility that the user made some typing error during typing the word. So the actual word wouldn't have spellings much different than this error word. So how we can find this words with similar spelling errors? We can find that using edit distance. And then secondly, we can use pronunciation. The words which have similar pronunciation to this spelling error could be the answer. But for this example, and in this lecture, we'll only generate candidates using edit distance. So edit distance is actually the minimum number of edits which are required to convert one string or one word to another word. So the minimum edit distance that you have studied so far includes 3 types of edit operations: insertion, deletion, substitution. So you can convert one string to another by inserting a character in that string, or deleting a character from that string, or substituting a character from that string. But in spelling correction, we'll add a new type of edit type, which is transposition of 2 adjacent letters. So while typing, a user can make the mistake of typing 2 adjacent letters at the opposite positions. So this is the 4th type of edit distance, and this is called Damer-Levenstein edit distance. I'm hoping that you know edit distance, or you can read it from this section in your book just to revise it. Edit distance of 1 between 2 string means that those 2 strings are only 1 edit away from each other. That 1 edit could either be an insertion or a deletion or a substitution or a transposition. So an edit distance of 2 means that those 2 strings are 2 edits away. It could be 2 insertions, 2 deletions, 2 substitutions, or it could be a combination of these edits. And for this example, we will only consider words within 1 edit distance of our error word. So this is the non-word spelling error. Acress is the error, and we want to generate candidates for this error. So actress is a probable candidate, and it is only 1 edit distance away from this error word, and that edit operation is, so if actress was the original word, T was deleted from that word and we got acress. Then cress could be another candidate. This is an example of insertion. So A was inserted at start of this to reach at this spelling error. Then we also have an example of transposition. So caress was the correct word, and we made a transposition of AC. And similarly, we have examples of substitution as well. So if excess was the original word, so this C was replaced by R. 80% of errors are actually within 1 edit distance, and almost all the errors can be found within 2 edit distance. So we don't need to go beyond that. And in addition to the insertion of alphabets, we should also allow insertion of space or hyphen. So for example, here user wanted to write this idea but wrote this idea like this instead. And we can also allow hyphen. Similarly, we can allow merging of 2 words. Database could be written as this, and if this space is omitted, it can be written as this. So now we have generated the candidates, but now we need to know which of these candidates are more likely to be the correct words. And for that, we need to go back to this noisy channel model and this language model. So now we'll study these two probabilities separately. So we'll see how we can get these probabilities. Let's first talk about the prior probability. This is probability of a word. This can be obtained by just training a language model. So let's say we train a Unigram language model. We have a large enough collection of words, document collection in this case, and we can count the occurrences of this word and divide by total number of tokens, and we can get the Unigram probability of this word W. We can use any language model. We can use Unigram, Bigram, Trigram, and we can also smooth these probabilities using either Laplace smoothing or interpolation. So that's how we get our prior probability. So this is an example of prior probabilities of these words, and it is coming from a corpus of contemporary English. So frequency of actress is this, and total number of words are these. So we can find probability of word P of W for all these words. Okay, now let's move on to the channel model probability, the likelihood part of our base law. Channel model probability is also called error model probability or the edit probability. So we have this misspelled word X. These are the characters of this misspelled word X, and we have a candidate word W, and these are the characters of this candidate word W. Now, as we are considering only one edit distance, the candidates which are only one edit distance away from the misspelled word, that means only one of these characters change. So maybe this W2 was written as X2 in the misspelled word, or this W3 was replaced by X3 in the misspelled word. So that is why it is called probability of the edit, because this is one edit. And the possible edits are deletion, insertion, substitution, and transposition. So to estimate this probability, we just need to know the probability of the edit that resulted in this correct word into the misspelled word. So if that edit was actually the substitution of W3 by X3, we just need to know the counts of this edit. So we need to know how many times this X3 was written in place of W3. And if we have those counts, we can estimate this probability. So to find the probability of edit, we just need to know the counts of these those edit operations. For that, we'll define a confusion matrix. Actually, 4 confusion matrix. One would be for deletion edit. The second type of edit is insertion. Third matrix would be for substitution, and the fourth matrix would be for transposition. So let's see what these confusion matrices actually have inside them. So let's consider this deletion matrix. So this deletion matrix actually has the counts when XY was typed as X. So Y is deleted from here. So the number of columns would be the number of alphabets, and number of rows would also be the number of alphabets. And we can fill this confusion matrix by counting in some data set how many times XY was written as X. That is, Y was deleted from here. Okay, about insertion matrix, we need to count how many times X was typed as XY. That is, Y was inserted here. For substitution, we need to count the times when Y was typed as X, and for transposition, we need to count the occurrences when XY was typed as YX. So insertion and deletion are actually conditioned on the previous character. Consider this, XY typed as X. So how many times this Y was deleted when it was preceded by X? So this is how it is conditioned on the previous character. To compute these counts, we need a corpus like this. So this is the correct word, and these are mistakes, which are only one edit distance away from this correct word. So we need to have a data set like this, which records a word and its possible errors. And from this, we can actually find the counts. For example, if we consider this example, or this example additional, so T is deleted here. So the user wanted to write IT, I is X here and T is Y, but wrote I instead. So T is deleted, Y is deleted in this example. This is a sample confusion matrix for substitution. So this is X and this is Y. So substitution of X for Y. Y was the correct character that user wanted to type, but wrote X instead. So if we see this entry, so user wanted to write E, but wrote A instead. And this happened 342 times. And if you look at the diagonal of this, diagonal actually means user wanted to write A and wrote A. That is not a mistake. That is a correct word. That is why diagonal is empty. You can generate your own confusion matrix. There's an online list of errors, and you can use that list to compute this confusion matrix. The link is given here. Okay, now that we have these counts in our confusion matrix, now we need to compute this probability. So if the edit operation was deletion, we can compute this probability using this formula, and if it was insertion, then we have this formula, and for substitution it is this, and this one is for transposition. So let's discuss this insertion formula. So user actually inserted an extra letter, which was Y in this case. So in numerator we have count of this mistake, that is how many times user wanted to type X but typed XY instead. We can get this count from the insertion confusion matrix, and we divide it by total count of X. If any of the entry of these confusion matrices is 0, that would make the whole probability 0. So we can use smoothing in this too. So in case of substitution, to find this probability, we add 1 to the numerator and we add A to the denominator, because there are A is actually the set of alphabets. So for every character we are actually adding cardinality of A number of ones. That's why we are adding A in the denominator and 1 in the numerator. So now we have all the counts for all these possible edits, and using these we can find this channel model probability using the formulas given on previous slides.